Now I am actually starting, and I think I wrote on the other one, not this one. I'm actually starting in section 11.2. We're going to do 11.1 on Monday. I just like teaching them backwards. All right, so this is a chi-square test of independence. The actual symbol chi looks like kind of a fancy X. That's chi-squared. We have two different chi-square tests that we're doing today that are math-wise essentially the exact same thing. So when to use a chi-square test of independence, this is when we take one sample.
Is our X supposed to look curvy like that?
That symbol is chi, yes. One sample from one population and then you're going to record two variables for each individual. This could be, I'm randomly selecting gentlemen students, and for each student, I'm going to ask them, what grade are you in, what's your GPA? That'll be two variables that I'm recording for each individual. But the big difference is here, between this one and the next order one, is I took one sample from one population, and then recorded two for each individual. So, what we are trying to determine here for independency is if they're independent or not. The null hypothesis, now I'm going to call one of these row variable and one of them column variable. It doesn't really matter which one I put first, but it's weird to write either one. So with the example I just said there, I don't care if you would say grade level and GPA, or if you said GPA and grade level, that part doesn't really matter. So the initial claim, the null hypothesis, is that they are independent. They're independent, they're not related. So what do you think is going to change about the alternative hypothesis? Not independent. So still the same things we're dealing with. If we have enough evidence, then they're connected somehow, which means they're not independent. And that part off to the side, you don't need to write that when you write your actual 4 steps. I'm just telling you that if they're independent, that means they aren't related. So we have a two-way table from a single simple random sample, which is what I put up here, one sample from one population, with each individual classified according to both of the two categorical variables. Conditions. We always have 3 conditions. What's the first condition? This is still random. When we do random, we check for what? Random selection, random assignment. I'm not going to write that right there for a specific reason. We know that it's both of those. What's our second one we usually do? Normal. Skip that right now. What's our last one? And what actually is independent? So when we are dealing with this, I am taking a group of individuals and I'm recording 2 separate variables on them. So would it make sense if I'm talking about GPAs and grade levels that I get to say that one thing is normal? So like we're dealing with multiple variables, right? So we can't just say the data is normal. So this deals with large sample size. One book says large size, and one book says large sample size. I want to make sure I'm writing the one that your book says. Yeah, it says large sample size. And I know you don't know what this means yet, but all expected counts. When we deal with things that are binomial, how do we check for normality or proportions? We have success and failure. How do we check for normality? So we make sure number of successes and number of failures are each at least 10, right? Now we're going to have a whole bunch of different categories. So they just have to be at least 5. So we need to make sure we have enough in all the different options, kind of like we did before with binomial or proportions. Alright, so the way you calculate test statistic is different. If you've taken biology, you've done chi-square stuff before, it's done the same way. So chi-square equals the sum of your observed minus your expected squared divided by expected. In stat, there's one thing that we deal with where we call it expected, and one thing where we deal with it, we call it predicted. So I might accidentally say the word predicted there, but it means the same thing. All right, and then somewhere, you might have more to the right than I do. We need to talk about how we deal with degrees of freedom. So when we deal with degrees of freedom, up to this point, degrees of freedom is just what? How do you find degrees of freedom? N minus 1. Well, now I'm going to have a two-way table, and I'm going to have a certain number of categories in each one. So I'm going to look at this like the way we do degrees of freedom. So I see how many of them there are this way, minus 1. I'm going to see how many of them there are this way, minus 1. And then I'm going to multiply those two together. So degrees of freedom is number of rows minus 1 times number of columns minus 1. So basically take off a row and take off a column, and then however many cells are left is our degrees of freedom. Alright, so to find our expected count, which you would have dealt with already if you were in biology, how do you find expected counts? Anybody from biology remember that? Alright, so up here, I left you space for totals. Let's do that really quick without wasting too much time. What's the 90 went in? What do I have here? 6, what? 1 what?
60.
What do I get for my next one?
41.
Next one. what I have for my high total? What's my middle total?
52.
And low total? For an overall total of?
3.
So we just found totals there. So if I am thinking about this cell right here, which of my totals deal with that cell? That cell deals with what totals?
211.
211 and 116 and 356. So I need to consider my row total, my column total, and my overall total. Does anybody from bio remember what to do here? No? Row total times your column total relative to the whole, so divided by the overall total, the table total. Instead of all of us doing these right now, you're going to have this group over here, find them for all three for high. This middle group, find them all for middle, and that side, find them all for low. So that we're all doing math, but we're not wasting time to practice all these.
What do we round to?
Let's go with 4 decimals, just because we've been pretty consistent with that. I'm going to do one of each, and I'll call them out, just so that you make sure that what you did was right. So you're just multiplying and dividing there to get the right thing. And then I'll call them out so we can all write them all in. So I'll go down now. For former, the current high that I wrote right here, just in case everybody can't see it, 68.7528. The high former is 83.5702. And below that is 58.6770. For middle, the one I have written down is 16.9438. For middle former is 20.5955. And middle never is 14.4607. 4607. For low current, the one I already have written down is 30.3034. The next one is 36.8343. And the last one is 25.8624. So you will definitely expect to see like multiple choice questions that say something like, how many would be expected to get for more middle former, and it would just be looking for that number. Now the next two-way table is taking both of these and using this equation. So observed is in my first two-way table, expected is my second two-way table. So to get this cell, I am taking what is my observed minus 68.7528, square that, and then divide it by 68.7528. Alright, so I'm going to give you one cell to do. So this row, your high current, former high, high never, middle current, middle former, middle never, low current, low former, and then I'll write the last one. And like I would write this for at least one of them, so when you go back and look at it, you have one that shows work, but I wouldn't obviously write it out for all of them. And then we're going to write them all in together. High current, what was my value? Keep it as 4 decimals.
4.5840.
4.5840. High former, what do I get? High former, what did I get?
0.1009.
I don't think so. Somebody get something different for that? Yeah. 8503. It probably was just where you put the square or you forgot to put the square. Never, I get what?
1.4813.
1.4813. Middle current, I get what? Middle current, I got what?
1.5.
Middle former, 0079. Middle never, low current, somebody did low current, 5.13197. Low former was what?
2.11.
And then the last one is 0.5768.
The observed value, was it for row or column?
It's just the cell value. Alright, questions with any of those, because I was only giving y'all one to make sure you did it, and most people weren't called out, so I don't know if y'all just weren't doing it, or you don't know how to do it. Do I need to go over any more of that? This is something that would definitely be a multiple choice question. It would say, how much does this cell contribute to the chi-square value? And you would have to put one of those numbers. Now, understanding what's actually going on here. We are seeing if what we are getting is actually what we expected, right? And we're finding the difference between them. We're squaring and dividing by and stuff, but we're finding the difference. So if I get a very small value, what does that mean with what I observed and what I expected? They're pretty close. This is about what I expected. I did a really good job. Whereas comparatively here, this one was the one that I guessed the worst. So I did the worst job, my model did the worst job at estimating what low current value would be. That's the one where I was off by the most. So a question that you would be asked is, what contributes the most to the chi-square statistic? This one is the highest value, so this one contributes most to the chi-square value because it has the highest, if I ask that question. I have it on a question on the back, I think, where I asked that. So in my equation, I just did this portion for each one of them. But what does this thing mean? So you're going to add them all up. Now, don't add them all up right now. I'm just going to tell you what it is. You just type all those in the calculator, you add them up. You end up getting $18.5097. For degrees of freedom, which I'm going to write out more than I need to. How many rows do I have? How many columns do I have? So I'm actually just doing what times what here, which is chi-square is a right skewed distribution, like that. So we are always shading this tail for a chi-squared. I am very briefly going to show you how to do this in the calculator. There's a reason I'm going over this pretty quick. Where do we go if I want to find the value of like an area for a normal? So second distribution, it's not normal, it's not t, so I keep going down. So I'm going to go to 8, which is chi-squared CDF. When I shaded there, what was my lower? 18.5097. What is my upper? Infinity, so 1E99. What is my degrees of freedom? 4. And we get a p-value of what? And I'm just because people looking at it to understand, it's 9.8 times 10 to the negative 4th, which means we're moving 3 zeros in front of that. Which means, what kind of p-value is that? A very low p-value, which means we're going to do what? Reject the null hypothesis. Yeah.
How do you know the shape right?
For chi-squared, it's always going to be. Chi-squared is always going to be shaded right. What's the question? Yeah. All right, so I want to go ahead and go straight into 4-step for this. No, I'm going to switch video and write the 4-step.